we're going to see if we can get an expression for the efficiency of a compressor. That's an adiabatic compressor, and by extension an adiabatic turbine. So if we have a PV diagram, and we're at some state P1, V1, T1, and I compress the gas adiabatically, that means P by V to the power gamma is a constant. Then I should come to P2, V2, and T2. And the area under the graph is the work done. Okay, so we can determine the work done by the integral. So I know P by V to the power gamma is a constant, so I can rearrange that equation, get an expression for P, substitute that in here. So my work done is constants times 1 over V to the power gamma, so I just C down on the V to the power gamma there. When I integrate it, that's what I get. Bring in V1 and V2 then, the definite integral, so bring V1 and V2 in, I get this expression. I'm just splitting this up using the rule of indices, so that's V2 to the power 1 by V2 to the power gamma, similarly with V1. And bringing the V2 to the minus gamma up. Okay, so we're multiplying it out. That's what I get. So multiplying this side by C, multiplying this side by this expression here. That's what I get. And then if we look at our equation, that's V2 to the power minus gamma. So that's the same as C over V2 to the power gamma and C over V1 to the power of gamma. And comparing that with here we have a constant is equal to P by V to the power gamma. So if I divide C by V to the power gamma, so I bring this down here, I'll get P. So I can say that this guy and this guy are P2 and P1 respectively. So I get P2 V2 and P1 V1 here. Okay, so I get two fractions. I can get the lowest common denominator. I get that equation, and multiplying above and below by -1, I get that expression. However, we know that from the ideal gas law, P by V is equal to MRT1 and MRT2 for P by 2V2. So substituting those in, I get MRT1 and MRT2. M and R are common to both sides. So I can say that the work done by the compressors is MRT1 T2. Right. If I compressed the air and I was 100% efficient, that's what would happen. But in reality, to get this amount of compression, I really have to aim up for somewhere here. Okay, I'm going to have to aim to compress the gas to this point where the temperature will be at T2 to have a compression ratio where the temperature should really be there, and we'll call this the ideal T2. Okay, so ideally that's where we would have compressed it to, and we would have been at that temperature. But in reality, due to inefficiencies, we're really going to have to aim to compress it up here to get this much out. And by aiming up there, the temperature will be this value here, T2. So that's the reality, this is the ideal. So the work out, what we actually get out, is MRT2 ideal minus T1 over gamma -1. And what we've put in is MRT2, so this work here. So efficiency is a measure of what we get out from what we get in, and it's just 1 divided by the other. They're all going to cancel, and I can say that the efficiency of the compressor in an adiabatic system is T2 ideal minus T1 over T2 minus T1. Similarly, on a turbine, if I want to get this out of it, I'm going to have to aim for there, and the compression, the the efficiency formula reduces to that, much in the same way as the compressor. And that's it.